All right, so this is, in my opinion, kind of more so of an introduction on mathematical models because we're going to be building them pretty much throughout the rest of the course from time to time. And essentially, what our author is intending for a mathematical model is basically a function that helps us model a real-world situation. Our first example already has a function provided for us, and in fact, it would be a piecewise defined function, one of our last topics on Monday. Whereas the other two examples we'll be working on, our models will be constructed on our own. And so we'll get some practice with, understanding some of the lingo, like what do they mean when they want a function of x, and how we use, well, the beginning problems, the ones in this section, will sort of rest upon some geometry. Nothing all that difficult, just some basic, formulas for, area and volume. But it's just kind of like a first exposure to it. As we go through the rest of the course, we're going to be building models, from verbal descriptions or from something called data. So introductory stuff, coming our way. But nevertheless, a really important topic because oftentimes, in the real world, if we're trying to, model a situation that is sort of mathematics related, the problem doesn't normally come solved, for us right away. So, we have to get some practice with translating some verbiage to the language of math, and that's what I hope for us to do in this section. So let's start with problem one, okay? A monthly tablet plan costs $34.99. It includes 3 gigs of data, which, by the way, this weekend I plan on starting a band called 999 megabytes. I hope we get a gig. But anyway, this monthly plan includes 3 gigabytes of data and charges $15 per gigabyte for additional gigabytes. Oh, how many times can we say gigabyte here? So the following function is used to compute the monthly cost for a subscriber. And so we have two different rules. First rule is the cost is going to be $34.99, and condition on x here, it says that you're going to pay this much if x is between 0 and 3, so inclusive of the 0 but not of the 3. So this condition right here says, all right, you're basically, if you use between 0 and 3 gigabytes, you're going to pay $34.99. Now, if you go over 3 gigabytes, you're going to be charged differently by virtue of Rule 2. We do 15 times however many gigabytes were used minus 10.01. Now, that's the cost formula if you use more than 3 gigabytes or exactly equal to 3 gigabytes. Now, we have a few parts here associated with our cost function. It says compute the monthly cost for each of the following gigabytes of use. So all these numbers here in parts A, B, and C represent different gigabyte amounts. In other words, these are specific values of x. So when you see 2 here, they're asking you to calculate C of 2. And just a reminder on how these piecewise defined functions work, you want to compare your input using these restrictions on x. So in the first condition or restriction, x is being compared to 0 and 3. And then in the second condition, it's being compared to 3 as well, just in sort of an opposite way. Now, here's our input of 2. Which of these conditions would it satisfy? Would it satisfy the first condition or second condition on x? Yeah, it satisfies the first condition, yep. So I'll note that 2 is definitely greater than or equal to 0, and it's also less than 3. So we would want to use Rule 1 to calculate this cost. And Rule 1 says, well, it's basically a flat rate there, all right, $34.99. And that would be the cost for using 2 gigabytes. And hopefully that makes sense, right? The monthly plan costs $34.99, and it includes 3 gigabytes of data. So using 2 would meet that criterion. Now for part B, going to be C of 5. Okay, which condition does our input satisfy this time? Second condition, you got it. Yep, 5 is definitely greater than or equal to 3. So we're going to want to use rule 2 to help us calculate this amount. So we'll do 15 times 5 minus 10.01. And when I calculated this ahead of time, I got $64.99. Why don't you go ahead and try part C, where there are 13 gigabytes of data being used. So for part C, we're calculating C of 13. 13, you probably found that that satisfies the second condition. So you plug it into the second rule. Looking at 15 times 13 minus 10.01. And this is kind of a shocking price here. I got $184.99. Confirmation on this value. That is, wow. All right, thanks for concurring, Kevin. Yeah, 13 gigabytes, almost $200. Ooh, telling you, that Fortnite is a data sucker, isn't it? Anyway, so that's our first model for this section. All right, we had a function provided for us, came in the form of a piecewise. The next couple of examples, we're going to kind of change the setting a little bit. We're going to be more, within the geometry realm. So this upcoming one, we're going to be blending some geometry concepts with the graph of an equation in the coordinate plane. And we have 2 coordinate planes here. The first is really to help us derive a formula, specifically an area formula. And then what we're going to do is we're going to take a look at the area formula's graph and see if maybe there's a maximum area. Now, what are we trying to find the area of? Well, as it says here, a rectangle has one vertex in quadrant 1 and so on and so forth. So we're going to be really finding the area of a rectangle, and as you're going to see, by way of construction, the area would actually be a function in x once we get to it. Now, it says here a rectangle has one vertex in quadrant 1 on the graph of y equals 16 minus x squared. We have another one at the origin, okay, so another corner, if you will. We also have one on the positive x-axis and one on the positive y-axis. So before we get to, like sketching out where these vertices or corners are at, it might be a good idea to have a sense of what this graph of 16 minus x squared looks like. And one way to generate a quick sketch of this is to maybe consider what the intercepts of this graph are. So for instance, with y equals 16 minus x squared, if you were to plug 0 in for x, you would get the y-intercept of 16. So what I'm going to do is put a point right here on the y-axis, and that would have the coordinates 0, 16. That would be the y-intercept of the graph. Now, can anybody think of x values that would turn this expression to 0? So in other words, what would the x-intercepts be? 4 or negative 4. Yep. Now, I'm only going to use positive 4 because based on the verbiage, this rectangle is going to be confined to quadrant 1. So I'm going to put a point on the x-axis for the x-intercept, 4 comma 0. And then what you would find is that this is kind of a U-shaped curve, basically a modification of the square function. And I'm basically going to draw a section of a parabola. So this is just a little chunk of this graph. The most important part of it is the part that's in quadrant 1 because, as we're going to see right now, we're going to be constructing a rectangle that's in quadrant 1. Now, let's go back to the verbiage here. It says a rectangle has one vertex in quadrant 1 on this graph. Now, it doesn't say any specific coordinates of where it's at on this graph, than the fact that it's in quadrant 1. So what I'm going to do is just select a random spot on this part of the graph. And because it didn't give us specific coordinates, best we could do is maybe just write it as x comma y. There has to be another vertex at the origin. So in other words, another corner of the rectangle is going to be at 0, 0. Another vertex has to be on the positive part of the x-axis. And in order for the shape to be a rectangle, the other corner, the one that's on the positive part of the x-axis, has to be directly below the point x comma y. And finally, we have one on the positive y-axis. So again, in order for our shape to be a rectangle, this will have to be level with the point x comma y. So here's our rectangle. And does the construction of the rectangle make sense so far? Any questions about where the vertices came from or the graph of y equals 16 minus x squared?
How did you know that that blue line was a curved line and not a straight line between the 2 points?
Yeah, so I looked at this right here, 16 minus x squared. From the library of functions, if you had f of x equals x squared, from the library of functions, that would be a parabola or a U-shaped curve facing up. And so since the y-intercept is at 0, 16, and we have an x-intercept at 4 comma 0, this is basically the graph of x squared just kind of turned upside down and elevated a little bit. And yeah, it's based on the square function, which is a U-shaped curve.
Got it. Thank you.
No problem. So there's our rectangle. Let's think geometry. Anybody familiar with a formula for area of a rectangle? Area of a square, area of a rectangle. Base times height, length times width. Yeah, I'll go with that one. So in general, the area of a rectangle is length times width. Now, if you notice in part A's instructions, it says express the area of the rectangle as a function of x. So what that means is the formula can only use the variable x. Currently, we don't have any x's on the right-hand side, but that's okay. This is just this is kind of the germ of the beginning, if you will. Let's take a peek back at this rectangle. If we want, we can consider the bottom part of the rectangle as our length and this vertical dimension of the rectangle as our width. Okay, switching those around won't really affect much, just to be honest with you. Now, the key here, there's a couple of key things to notice here. The length part of the rectangle is actually given by the x-coordinate of this point, x comma y. And think about it, if we start at the origin and we want to get to the point x comma y, we'd have to go to the right by x units. So the length of the rectangle would be x. How far up would we have to go to finally reach our destination of x comma y? Yep, we'd have to go up y units to get to that point from the origin. So our width is going to be given by the variable y. And this allows us to modify our area formula. We could rewrite it as x times y. There's still a minor issue though. Our formula can only use the variable x, which we finally have x in the formula, but we have to figure out what to do with this variable y. Now keep in mind the point x comma y is on the graph of y equals 16 minus x squared. So any point that's on this graph, its y value can be calculated by using the formula 16 minus x squared. So what we're allowed to do is replace this variable y with the expression 16 minus x squared because this point is on that graph. Does that make sense? So what you can do is keep x as x, but the variable y can be replaced by the expression 16 minus x squared. And that all has to do with the fact that that point, or that corner of the rectangle, is on the graph of 16 minus x squared. What I'd like to do from here is distribute the x. That will give us 16x minus x cubed. And just to have this in standard form, I'm going to switch the terms around, negative x cubed plus 16x. Now, once we substituted the variable y with the expression 16 minus x squared, the formula involved only the variable x. So at that stage where we substituted 16 minus x squared in for y, we actually did have, and currently still have, a function of x. So I'm going to add a little bit to our capital A notation on the left. I'm going to write this as a function of x. So function notation there. And this would be our formula, which gives the area of our rectangles that we could form in this way. Okay, any questions about that? Let's talk domain. So the domain of our area function if we were just in, a basic um, function domain setting, outside of this context of a real world setting or application setting, our domain would appear to be all real numbers because there's no division by zero possible or, square roots. But we got to keep in mind our context. This is a formula giving us the area of all the rectangles that can be formed in quadrant 1 in this way. This isn't the only rectangle that can be formed. You could scooch this point x comma y along this little arc, and you can construct different rectangles. And because we're going to get different, sized rectangles, there are going to be different areas for each one. Now, this rectangle has to be in quadrant 1. So based on that, we can assume that x has to be greater than or equal to 0. But does that mean our domain is anything from 0 to infinity? Do you maybe think that there's like a maximum possible value of x? So keep in mind that the rectangle has to be in quadrant 1, and one of the corners always has to be on the graph of 16 minus x squared. In order for that to happen, the only x values that we could possibly use to satisfy all those conditions are going to be those between 0 and 4. Any x value past x equals 4 will kind of move our rectangle, or maybe even make it possible to construct by trying to satisfy all the conditions here. So if we want our rectangle to be situated in quadrant 1 with one corner on this graph, we're not really going to be able to go past x equals 4. We'll probably get something that we couldn't construct, based on the verbiage. And we also couldn't have x being less than 0 because, again, we're confined to quadrant 1. So x has to be greater than or equal to 0, and x has to be less than or equal to 4. You can mesh this together in the form of a compound inequality as 0 is less than or equal to x is less than or equal to 4. But I would prefer interval notation, bracket 0, comma 4, bracket. Okay. Any questions so far? Alrighty. Well, for part B, we're going to graph our area function. And we'll do that in the graphing calculator. And basically, in y1, we're going to enter our expression for a of x, which is negative x cubed plus 16x. Now, before we get to the graphing calculator, let's look at what it's asking for. It says for what value of x is a largest. Okay, so this right here, for what value of x is a largest, is kind of instructions for find the maximum. And when I get to some window setting recommendations, and we graph the equation with those settings, you'll see that there actually is kind of like a highest point on the chunk of the graph that we hone in on. And so let's talk about some window settings that might be helpful here. Based on our domain, we know that the minimum x value is going to be 0. So that's how I would know to set x min to 0. What do you think our x max value will be? 4. Yep. And we can leave the x scaling at 1. Keep in mind what the y values represent. The y values here represent different areas. So we probably don't want any negative y values to be considered. So I'm going to set the minimum y value to 0. As for the y max, here's where I'm going to kind of break away and get this equation typed into the graphing calculator, because I have kind of a clever way of figuring out what to use for y max that I'd like to share with you. Okay, so let's go to the graphing calculator. There we go. All right, so in y1, negative x cubed plus 16x. Let's press the window button. We'll adjust some of these settings according to what we just wrote down. So 0 for x min, 4 for x max. We can leave the x scale at 1. Y min will be left at 0. And then for y max, let's take a peek at the table that the graphing calculator constructs whenever you enter an equation in. And to access the table, you're going to press the second key, and then you'll hit the graph button. Now, if you look over in the second column, these are different area values. And you can see that, the very first area value is 0, and then, when we use x equals 4, the last area value is 0, but we get some positive areas in between those two zeros. And look at this, anything past 4, is starting to give us negative area values. So that's kind of another indication as what our domain should be. Now, if you look at the y values that are between the two zeros, they range from 15, 24, 21. I would probably recommend using a y max value of at least 25. If you want to kind of overshoot it a little bit, maybe use 30. But you don't have to go any higher than that probably. Okay, so let's go back to window. And for y max, just to give us a little more cushion to work with, I'm going to change y max to 30, and then maybe go by 5s on the y-axis just so that it's not super thick. All right, so everybody make sure you have those settings, and then press graph. And you guys getting similar looking graph? Rock on. So if we just hone in on this section of the graph, it would appear as though we have a maximum. And on Monday, we saw how we can use the graphing calculator to help us find that maximum. So I'd like to review those steps. Let's press second trace. And we'll go to option 4. And press enter. And you may recall that it's kind of like the 0 feature where they want left bound, right bound, and a guess. But when we're talking about maximums and minimums, we're really referring to like the left-hand side of the max and the right-hand side of the max. So we're not really going to fiddle around with the x-axis. We're really just going to put our blinky cursor on the areas that are to the left and right of our high or low points. Where I'm currently at looks pretty sufficient for left bound. I'll press enter. And then I'm going to scooch over to the other side of the hill, if you will, and press enter. And then for guess, we just move our blinking cursor, as close as possible to that high point. And can I get a confirmation of 2.31, comma 24.63? Woohoo! All right. I'm going to go back to the notes here. We got some catching up to do with our little diagram. First of all, we set y max to 30 and went by 5s on the y-axis. I'll indicate some of these tick marks. The x max was 4, y max is 30, and our graph, a little something like this. And the maximum was at roughly 2.31, comma 24.63. A couple other things I'd like to add here are labelings of the axes. Okay, going along the x-axis are our x values. And then going along the y-axis are the area values. Now, 2.31, that is the value of x. That's kind of like the sweet spot here. If we scooched x over from the origin to roughly 2.31, we would construct a rectangle that has the largest area of all the possible rectangles that can be drawn, according to the diagram in part A. The y-coordinate would tell us what that maximum area truly is. So I'm going to put a tick mark on the y-axis, 24.63. I'll label it as. And that's the highest value of the area, of all these rectangles that can be formed this way. So it's kind of like an absolute maximum, if we just consider this part of the graph. So let's see what the instructions are asking us for. For what value of x is a largest? Technically, that's referring to 2.31. So I'll say x is approximately 2.31. And although it doesn't ask for it, I do want to make a note that the max area is approximately 24.63. Okay, questions, comments, concerns, winning lotto numbers, anything like that?
Wouldn't the max area be 2.31 times 24.63? Because isn't 24.63 just the height?
This is the graph of the area function. So all of our values of y on this graph are different areas. So any y coordinate on this graph will already have the area calculated beforehand. Like if you wanted, you can arrive at 24.63 by plugging it into y equals 16 minus x squared. So let me see if I can jot that down somewhere. If we did 16 minus 2.31 squared, that would be our height. So let's see what that comes out to be. About 10.66. And so our rectangle would have a width of 2.31, and its height would be given by 10.66. So let's see what we get when we multiply those two out. .49-ish. So it's close to what the graphing calculator gave us, but keep in mind there was some rounding here beforehand. Specifically, 2.31 was rounded, and I rounded 10.6 as well. And actually, you know what? Let me type it as 10.66. Oops. And that's a little bit closer. There we go. So really close to what we got from the graphing calculator. It's just a tad off because of our rounding, or my rounding, I should say. But yeah, the height is actually given by the equation 16 minus x squared. Because if we look at our first diagram, okay, our first diagram is where our rectangle was constructed. And so the length, or the base, is given by x, and the height, or the width, is given by y. And so if we wanted to calculate the height of our rectangles, we would plug the x values into the equation 16 minus x squared, because that's what y stands for on this graph. Is that making sense? No problem. Alrighty, anything else, folks? Then let's get to our last problem. A sort of geometry type problem, but we won't be in the coordinate plane. It says here an open box with a rectangular base is to be made from a piece of sheet metal 16 inches long and 14 inches wide. And how this works is that there's going to be a square of equal size cut from each corner. And when you remove those square corners, you form, like 4 flaps, which end up being the sides of your box. And so I have a couple of diagrams for us provided already. And we're going to mark these up with some dimensions, and we'll use the dimensions to help us calculate expressions for the side lengths of the box itself. Now, the piece of sheet metal has to be 16 by 14. So with this first rectangle, all the way from the left-hand side to the right-hand side, that's got to be 16 inches long. And then from top to bottom here, it's got to be 14 inches wide. Now we have to remove a square from each corner. It doesn't tell us what the size of the square is, so this is where we're going to get some variable, well, get a variable introduced into the problem. Just to make it easy, let's have the squares have a side length of x. So I'll focus on this upper left-hand corner. If this is a square and one side of it is x units long, then all 4 sides are x units long. So I'm going to include another x right there, and you'll see why in just a minute. So this x by x square is getting removed to help form a flap. There's another x by x square in the upper right-hand corner that gets removed to further help develop these flaps. And actually, all 4 of these corners are getting removed, and all 4 of these corners are x by x squares. And so what would be left over, it's kind of like a net diagram of the box that's supposed to be formed. Now what I'm going to do is sketch out the rectangular base that they referenced. And that rectangular base can be sketched out in the following manner. And it kind of makes it a little more clear as to how the sides are being formed. We get four flaps that basically get turned up. Now, part A wants us to express the volume of the box as a function of the length x. So here's where it can get a little dicey. The length of our box, maybe if we assume that this is our length, that's not going to be 16 because the flaps had been formed beforehand and turned up to make it. So we should probably see if we can find an expression for the length of this box. And the clue is with the 16 and these two x's that are on either side. Now, if it starts out as 16 inches long, and we remove these x by x squares, the length of our box is going to be given by the dimensions of this part of the rectangle. Can anybody come up with an expression for the length of this rectangle? Perfect. Yep, 16 minus 2x. Right on the money. Does that make sense, folks? If it starts out as 16 and we take away x on one side and x on the other side, then we've reduced 16 by 2 x's. So the length of our box will be 16 minus 2x. Let's assume that this is the width of the box. And that would be given by maybe this part of the rectangle. It's no longer 14 because it's been reduced by a pair of x's. Can anybody come up with an expression for the width of the box? Or in other words, the width of the rectangle? Well, it starts out with 14, right? And we take away an x from each side. So perfect, yep. It's going to be 16, I'm sorry, not 16, but 14 minus 2x. So the volume of the box needs 3 dimensions: a length, a width, and a height. Any suspicions as to what the height of the box might be? Okay, that's close. I'll give you a little nudge here. I actually had this. Where's it at? Here we go. I actually have something from my math lab that was added to the new edition of the book. With a similar situation that we're looking at right now, where we have a rectangular base and we remove, x by x squares from each corner. Theirs are in yellow, and I have these sliders that are gonna help me to help you guys with figuring out what the height of the box is. Now, this is for a 20 by 32 piece of paper. And so I'm gonna click this show dimensions here, maybe rotate it. Yeah, I'm just gonna recalibrate it here. Okay, so 32 minus 2x, because the original length was 32. 20 minus 2x, because the original width was 20. And then there they had their x by x squares, or at least one of them labeled x by x. What's really cool about this is that you can have a fold, or you have a slider that allows you to fold up the sides and kind of put it down this way. As I continue further and further to the right with this fold slider, you can see the sides forming by being turned up to form that open box. Now, maybe keep an eye on this section of the diagram where we have the x by x square marked. I'm going to start over. So the x by x means that this little corner that's been cut out would produce a flap that's x units high, and actually that would be the height of all the flaps. And here's a little visual of why that is, or at least visual to help convince you of that. The size of the square that you remove dictates your height. And I'll show this again, maybe with a larger square cut from each corner. Form the 4 flaps that way. And again, we see that the size of the square dictates the height of the box. Does that make sense? All right, cool. If this were an in-person class, I would actually have like manipulatives for us to use. It's a little hard to do virtually though, so I'm really glad I was able to find that little slider thing. But normally what I would do is I would have like a different size pieces of paper cut out, different size corners, and then I would have you folks cut them out and try to form a box and everything, and you'd be able to see in real life how the size of the square dictates the height. So like I just makes me want to be in class even more doing this section right now. But anyhow, the height of the box will be given by x. And that helps us pick up some steam here. They want us to express the volume of the box as a function of the length x. And just based on a geometry formula, volume is length times width times height. 16 minus 2x can be considered an expression for length, 14 minus 2x for width, and then x for height. And what I'm going to do is I'm going to replace all of these variables here with these expressions. I'll use parentheses since a couple of them have a couple of terms. 16 minus 2x times 14 minus 2x times x. Now, just to save on some time, I do have the right-hand side fully multiplied out, and we'll provide it for you. This works out to be 4x cubed minus 60x squared plus 224x. And this would be our formula for the volume of the box, which depends on the size of the square that you're removing from each corner. So as soon as you tell me, what size square you want, I'd be able to plug it into this formula and provide you the volume, okay, the amount of cubic units, in this case, cubic inches, that could be held within the box. And in fact, parts B and C want us to do just that. They want us to figure out what the volume of the box would be with these different size squares. All right, can I give you a couple minutes to maybe work out parts B and C? And then I'll help us get going with part. All right, I'm going to jot down my work for part B. Let me know if you have any questions along the way. It says here 3-inch square, so that's a particular value of x. That's going to get plugged into our volume function. And I got something to the tune of 240 inches cubed. What about you guys? Sweet. Well, very similar thing for part C, 5-inch square. It's x equals 5. Anybody want to offer what they got for x equals 5? What do you guys think about 120 inches cubed? So why do you think that might be? Why the decrease in volume? We went from a 3-inch square to a 5-inch square. Intuition might lead you to believe that it increases the volume, but we actually see a reduction in volume. Any suspicions as to why that might be? If we go back to that little demonstration here, I'll restart it. As x increases, it affects the dimensions of the base and the flaps. And so, you know, as x increases, there's actually less material that you have in order to form the box. And so that's probably why the volume is impacted in that way. But then again, you know, when x is pretty small, you know, you don't really get, you know, that tall of a box. So, you know, starting out, the volume might be small as well. So anyway, there are some varying volumes depending on the size x of the square that you remove from each corner, which probably means that there might be a largest volume that can be calculated. And that's what part D is all about. They want us to graph this volume function and then figure out, what size square would give us the largest volume. So in Y1, we would enter our equation from part A, 4x cubed minus 60x squared plus 224x. And I'll provide some recommended window settings. I would recommend using 0 for x min. Okay, we wouldn't really be able to construct any negative side length of squares. The maximum x value is going to be 7, and the reason for that is because one of the dimensions is given by 14 minus 2x, and so if you use values of x that are larger than 7, we start to get some negative side lengths of the box. So you'll want to cap it at 7 for this problem. You can go by ones. Keep in mind that the y values represent volume for this graph. So we probably don't want to consider negative volume, so I'll put y min at 0. And then again, kind of playing around with that table, I found that y max of 250 was sufficient enough to see the maximum. And then I just went by 50s for the y scale. So can I have you folks take a couple minutes to get this graph going in your calculator with these recommended window settings, and once you have it there, see if you can find the maximum. Okay, I'll give you a few minutes to do that, and then we'll take our break. All right, I'm going to do my best to sketch out something resembling what my graphing calculator gave me. You guys getting a similar shaped graph? All right, was anybody able to identify the coordinates of the maximum? Awesome. Nice job. Yep. 2.48, comma 247.51. Now 2.48, that would be the value of x, or the side length of the squares that give us this maximum volume, which the maximum volume, if it asked for it, would be 247.51. So they're only asking for what value of x. So technically, they only want the x coordinate for this problem, say 2.48 inches. But it's worth noting that the max volume, I'll say max V, is approximately 247.51 inches cubed.